Hi, this is Dr. Hassan Abdullah with the course Complexity and Analysis of Algorithms. The topic which we are covering is divide and conquer algorithms, and the subtopic is applications of those algorithms. So, this is video lecture number 4D. So, 4 is the topic and D is the subtopic. So, we already had lecture 4A, B, and 4C. So, this video is based upon using the supplemental material available at easymcq.com/goget, and this basically is a learning management system with personalized features. For example, personalize your level of learning. You can also personalize your experience of viewing and interacting with the portal, and you can also have personalized level of online testing also. So all of these wonderful features are explained in these 6 videos, 1 through 6, and these videos and the course material and all the videos are available on my YouTube channel. So if you search for Dr. Asan Abdullah, you will get these 6 videos and the remaining videos of this course also. So what does this course covers? The course consists of state of the art content. So the material is up to date and diverse material including advanced algorithms, also randomized algorithms, approximate, and genetic algorithms. The topic which we are covering in this video is divide and conquer algorithms. So now we move on to the supplemental website. So we have already covered 15 Q&A in 4A and 4B parts of divide and conquer approach. So now we are in 4C. So we are at the question and answer number 16. So how divide and conquer approach used in binary search? Okay, it is extensively used in binary search. So there is the divide part, which basically we look at a half of the data to be searched and disregard the other half. I'll explain it to you. So that is the divide part, and then we do the conquer part. The conquer part is we perform the search. Okay, and this is the step 2. And then of course we perform the combined part. Basically combined part is not as in traditional combining. Basically we are just doing it recursively. So let me look at and show you to you. So divide the search space, and it would be better if I turn on the pen also. So the divide is divide into two halves by calculating the middle point. Of course that doesn't have to be exactly the middle. If it's sufficient that it is by difference of a 1. And the middle element divides the array into two sub-arrays, and they are not required to be of equal size. Okay, the middle element is compared with the target value, right? And depending upon the target value, which is in which half, so the working shift to that particular half. So for example, if this is the data set which is sorted, okay, so I divide it, right, and divide it with the middle value over here. And if the data which I'm looking for, that particular number says to say, if it could fall here, so this is disregarded. And then I divide this as per this is the middle value 1, I can call it. This is middle value 2, and check it. Maybe it doesn't fall here, so it could be here. So this is how it works. And the search continues to the left half, and it keeps on going. And of course it could be the right half also. So that is the conquer part. So the combine is not really needed in the traditional sense which I mentioned, because it's a divide and conquer approach, so we call it the combine part. So as let me clear this for you. Okay, so as we mentioned before that in quicksort, and we'll do it again, there is no real combine part. Combine part is there in merge sort. So the combine service is not really needed in the traditional sense, because we do not really combine. But the problem, the size is reduced, of course, which is the property of recursion. So what are the steps? I've explained the steps to you. So if we go on to this figure, so let me turn on the pen. So I'll go into more detail. So this is the about the middle. Okay. So depending upon the middle, we have two divisions, right? And then what we were looking for, that could be either in this partition or it could be in this partition, but of course cannot be in both partition unless all the values are the same or they are right. So then we divide it, and this is the way we keep on dividing it till we find the number which we are looking for, if it really existed or it exists, or we will not get it. So our purpose is served. So this is how it works. Let me clean this for you. And of course, if you are interested in more, these are the references. Okay. So let's now do a more concrete example, right? So we have this data set, okay, and as you may notice that this is sorted, because otherwise it would be a brute force approach and it will take order and time if it's not sorted. And if it's sorted, then it takes order, log, and time. And this we have also shown through the application of the Master's theorem also. So let's work on it. So we have the low index as per the way it is implemented, which is basically telling us the size or the starting point, and the high index is the last index of the array. So this is 0, 1, 2 up to 9, which is like 10 values here. So calculate the middle value. Of course, this is the approximate value 4, right? And in this case, it is actually you can 0, 1, 2, 3, and 4. This is the one. Okay, so the target value is 46. We compare with 46 and we see that it's not possible. We have 32 here and we are looking for 46. So there's no need to look at the left part, right? So then we change how we divide it, and it is the seventh value. The seventh value is 112. We look at it and soon we zero in and we get what we are looking for. So if I zoom this for you, okay, and turn on the pen, just give me a second, right? I have the pen. So we looked at this. This is the data set. This is the middle value, right? And we compared with 46, and we saw that 46 is greater than 32. So there is no need to look at this area. There's no need to look at this area. So we are basically cutting down the search space by half. So that's why the time complexity is logarithmic. Then we look at the middle of this part, and we see it's 112. So this part is not looked at further. So that's the way it works. So let me clean this, okay, and zoom back. All right. Okay. Let's move ahead. So that was, so we looked at the shortest, the closest pair problem, and we briefly looked at the binary search. So the most of the remaining lecture is about merge sort and quick sort. So what is merge sort and how does it work? So this is pure divide and conquer, with the pure division and conquering and combining everything goes here. So divide, conquer, merge operation. So basically divide the unsorted array. It is unsorted into two halves, right? And you keep on dividing this. This process continues till no further division is possible. So let me turn on the pen. So this process continues till no and base case is reached. Now the recursion stops. Once divided the single element sub arrays, so then we merge those sub arrays, single ones. So we end up with array size of 2, and then we merge array size of 2, so we end up with array size of 4, and so on. And this merging takes order and time. Okay, so let me clear this from here. Okay, so that was the conquer part, right? Merge operation is order and time. So this operation is performed iteratively. This perform is iteratively. So you can say, or you might say that if it's iterative, okay, so where is the recursion? Where is the recursion? Where is the recursion? Pardon for my writing, not very elegant, especially with the digital pen and a tablet. So where is the recursion? So that recursion was there to the base case. Okay, now that merging takes place, and that is iterative. Okay, that is iterative, and it could be depending upon sorting in ascending order or descending order. It is repeated till all elements from both sub arrays are merged. Both sub arrays means that that whatever that partition size could be, starting with partition size of when we are merging, starting with the partition size of 1. Okay, let me clean this. Okay, so I will zoom it. Actually, there's no need to zoom, but still I would zoom. Okay, let me turn on the pen. All right. So we have this problem. We split it into sub problem, say 1, and this is sub problem 2. Okay, and then we keep on splitting this recursively till we end up with very small problem sizes, and then we solve these problems. So this is bidirectional. So you split and we merge. Keep on splitting it. Keep on splitting. Okay, and then we merge them together and we go back and we have the problem solved. So let's go. Let me first clean this. Okay, and look at it in more details. Okay. So pseudocode and explanation of merge sort. So the pseudocode is here. Okay, the pseudocode is here. So we have if the length of the array is greater than 1, then we find the middle. This has to be approximate, divided into two parts. Okay, and then we keep on dividing it, right? Then till we end up with one cell size, and then we perform the merge operation. So this is the pseudocode. The explanation is already given here. It's very simplified. It's not complicated. So this is very interesting for your ease of understanding. There's an animation. So please look. So this is the data set. We keep on dividing it. So from 8 to 4th and to 2 and to single. Okay. So we are down to single now. Okay. And then they are moving. Okay. And they are combined. So this is the merge operation. So merge. This is merge is happening here. These are merge operations. Okay. This is merge operation. This is again a merge operation, right? Then they are going to be merged. See, this is again a merge operation. So this takes order and time. This takes order and time. This merging takes order and time. And of course, you see that the data size is so we have 1, then we have 2, then we have 4, and finally we will have 8. So and then of course they also need to be merged. So they are merging. The merging takes place over here, and finally we will have the sorted solution. So with this, we move on to the next part of the next set of the